Okay, welcome back. So last time we left off with talking about lines in R3 and how we kind of found two different ways of discussing these lines, describing them, either using parametric equations where we had a starting location given by a vector r0, and then we had a parallel vector v that we use along with a parametric variable t to kind of help us go along that line. We also kind of eliminated this parameter t by having all three x, y, and z equations equal to t, and then we got from that the symmetric equations for the line. So now, today, we're going to talk about planes. So a plane can be described by a point and what we'll call a normal vector, which is to say a vector that is orthogonal to all vectors on the plane. So let's kind of sketch this out. Imagine that maybe, let's just draw with lines. We've got why don't we actually just do a copy and paste? So we have some plane here, and the idea is I have some point here, and then I'll have some vector that points right off of the plane. So this is the point that we'll call P. We'll have some vector that we'll call N, and it is orthogonal to every vector that's in the plane, right? So any vector that comes out of P, it's still going to be, that's on the plane. We're going to have 90 degrees to it from that point in this vector direction N. And that's all we need. We just need the point P and the N vector, and we have enough information to describe what this plane is. Okay. So from that, can we kind of decipher what the equation of a plane might look like? Well, notice if we let R0 equal the vector that goes from the origin to the point P, then we know that the vector N dotted with the vector that we'll call R, which is any arbitrary vector on the plane. So we can say that these all are candidates for this R vector. Then R minus R0 is a vector that describes any vector that is possibly on the plane is equal to 0, right? Because they have to be orthogonal. So imagine here, actually this is probably, let's do it like this so it's easier to kind of illustrate what's going on here. I have some origin. And now what we've done is we have R naught that points to this point, and then we have R that points to some other arbitrary point on the line. So this vector is R naught, and here we have R. So if we subtract these two, we get the vector that's on the plane, and any arbitrary vector that's on the plane is orthogonal to our n vector, our normal vector. So that means that the dot product between the two is equal to 0. Or we can rewrite this as n dotted with R is equal to n dotted with R naught. Right? I can distribute this dot product, and I'll have minus n dotted with R naught, and I can just move that over to the other side. So in terms of components, so let's look at the x, y, and z portion of this. If we wrote n as some a, b, and c, so this is our n vector, and we're having it dotted with r minus r naught, which is x minus x naught, y minus y naught, and z minus z naught. Well, we said that this dot product was equal to 0. So this is here our r minus r naught vector. Can you please go back up? Here's what we're doing right now. We're just looking at the dot product of our normal vector with any arbitrary vector on the plane. So let's kind of do out this dot product. What happens here? Well, this is a times x minus x naught plus b y minus y naught plus c z minus z naught, parentheses, is equal to 0. So what I'm going to do is if I say by letting we are disconnected. Okay, hang on. Sorry about that. I think I lost internet for a second there, but we're back. Let me pull up the chat. Okay, so what we're going to do is we're letting all of these constants, so a times x naught plus b times y naught plus c times z naught equal some constant d, right? If we just FOIL these out, we've got this a x naught is y and b y naught, and then c and z naught. I'm just going to let that be some new constant d. So then I get the resulting AX plus BY plus CZ is equal to D. So this is the equation of a plane. We have 4 different constants that we need to lock down, this A, B, and C, as well as this constant D out in front. So notice this is a linear equation in X, Y, and Z. Right? What I mean by linear is that our powers here don't exceed power 1, and there's not any like cosine terms or sine terms, any trig functions. This is just a linear polynomial at best, right? Because we've got some constant terms and some power 1 terms. And that kind of makes sense if you think about it, right? A line in R2 was a linear equation. Well, in R3, a linear equation represents a plane. So kind of, let's back up a second so we can note something here. This A, B, and C was what I wrote for the components of our n vector, right? And notice that they're coefficients out in front of X, Y, and Z. So that's a quick way to go back and forth between the two, right? If you know the vector n is some ABC, you know those immediately are the coefficients out in front of our linear terms x, y, and z. Vice versa, if I give you the equation of a plane, you can read off the normal vector very easily. It's the vector a, b, c. So let's just kind of reiterate that in text. So note, the vector A, B, C is the normal to the plane AX plus BY plus CZ is equal to D. So that's really handy. So now let's do an example where we're asked to find the equation of a plane. So we're going to find the plane with points A at 0, 0, 1, the point B of 2, 0, 0, and the point C, 0, 3, 0. So might be asking yourselves, okay, I just said that we needed a point and a vector that defines the normal to kind of describe this plane. Well, we still have that here. We have 3 points, which you can imagine defines this plane, but in this is the normal that we can describe. Okay, well, what do I mean by that? How do we get the normal from these 3 points? Right? Well, we have a point, right? And all we need is this vector that kind of defines this normal. But we learned something in the last section about finding a vector that's orthogonal to 2 other vectors, the cross product. The cross product allowed us to take 2 vectors and find a vector that was orthogonal to both of those. So all we need to do is find 2 vectors that are in the plane, or some vector that goes from A to B and then A to C. So to kind of just reiterate in text form here, so to find the normal vector, we find the cross product of two vectors on the plane. So let's go ahead and find two good candidates. So going from point A to point B will give me the vector 2, 0, -1, right? Because I'm subtracting the vector that points to A. Sorry, I started, so I end up at B, so 2, 0, 0. I'm subtracting the vector that points to A, 0, 0, 1. So I get 2, 0, -1 here. And then I'm also looking at a second vector that lies on the plane, the vector that goes from A to C, which is the vector that points at C, 0, 3, 0, minus the vector that points to A, 0, 0, 1. So we'll get 0, 3, -1. So these are two vectors that are on the plane. And we could have done different combinations. We could have done B to C. That would have been another perfectly fine candidate. But these are now two vectors on the plane. And if we take their cross product, we'll generate a third vector, but this one is going to be orthogonal to these two, right? So we'll say that n is equal to AB crossed with AC. So we have to do our cross product here. So we'll have an I hat, we'll have a J hat, we'll have a K hat. We'll have 2, 0, -1, 0, 3, -1. So in the x component, we have the determinant of this lower block here, or 0 times -1 minus -1 times 3. So we'll just have a 3 here. Now we do have to keep in mind that we're going to do the negative for the j. So we're looking at the determinant that's the 2, -1, 0, -1. So this gives us a -2, and this just gives us a 0. So we're just looking at a +2 here. And then for the z component, or the one on k hat, we're looking at the determinant of this lower block, or 2 times 3 minus 0 times 0, or just 6. So our cross product is just 3, 2, 6. And this vector is pointing orthogonal to our plane. Okay. So now all we need is just a point that's on the plane. Well, any of our points A, B, or C will work perfectly fine. I'm going to just choose A. So then we have 3 times x minus 0 plus 2 times y minus 0 plus 6 z minus 1. And this is equal to 0. Right? So this is our n vector, 3, 2, 6. And then our x naught, y naught, and z naught are from our point 0, 0, 1. So we can FOIL these out. And we'll end up with 3x plus 2y plus 6c is equal to 6. And that's the equation for the plane that includes those 3 points A, B, and C. Right? So it's not too bad, right? Even though we didn't have this vector available to us, we could easily find it by finding two vectors that are in the plane and using the cross product to give us a vector that's orthogonal to both of those, meaning that it's orthogonal to any vector in the plane. Okay, so we talked about the distance from a point to a line. Well, this time, let's talk about the distance from a point to a plane. Oh, we have a question. Why is the x component 3? The x component is 3 in the cross product because we're taking the determinant of this lower block here, which is 0 times -1 minus 1 times 3. So we'll just have a 3 there. Okay, so let's kind of sketch out a plane here. Something like that. We'll also have 2 different points. We'll have one that is off the plane. Keep doing the straight line tool. There we go. And then we'll have another point, arbitrary point, just like we did with the line, that is on the plane. And then we'll have some vector that goes from the point out. We'll also have some point that's directly beneath the point that's on the plane, and a vector that points orthogonal from the plane out to this point here, and that the magnitude of that vector will be the distance from the plane to the point. So we have the plane that is detailed by ax plus by plus cz is equal to d. We'll have some point p0 that is on the plane. We'll have some point p1 that is above the plane. And point 1 consists of x1, y1, and z1. So I'm not going to go into the whole proof about the distance here, but it's a little drawn out. But the distance here is going to be the magnitude, the absolute value of a x1 plus b y1 plus c z1 plus d all over the square root of a squared plus b squared plus c squared. There's actually a number of ways that you can prove this. One way is to find the normal to the plane, the A, B, C, and then take that normal, start at your point P1, and then scale it until you hit the plane. And then that's the magnitude that you need. Another way is kind of similar to the line, where this point P0 will share a line with the point that kind of goes with it. Can I not move one side of that line? Oh, unfortunate. But they'll share some kind of line here like that. And you can do kind of a similar argument for that. Is there a disagreement of signs of D in the two expressions? Meaning, is this supposed to be a negative? I believe that it's supposed to be a positive here. Okay. So with that, we're going to move on to 10.6. So 10.6, we're kind of leaving behind the lines and planes and kind of opening ourselves to more general surfaces. And we'll kind of talk about what these look like and get a sense for them. So we looked at linear expressions here. Maybe we'll look at quadratic surfaces. So let's do a new page. So 10.6. Where we're looking at cylinders. And quadratic surfaces. So you might be thinking to yourselves, I know what a cylinder is, right? You kind of think of maybe like a soda can, right? Oh, that's a cylinder. Well, I hate to break it to you, but the way that math defines cylinder is a little bit different. So let's kind of go through what that definition is. So a cylinder is a surface that is composed this is quadric. This is quadric surface. Yeah, not quadratic. Of all lines that follow two guidelines, lie parallel to a given line in space and two, they all pass through a given plane curve. Okay, so let's talk about what you might consider a standard cylinder. So let's kind of draw some axes here. So I'm going to try my best here to kind of draw a cylinder. So we have something like this. Let's make it closed. Oh, you know what? Let's just do straight lines for those ones, huh? Something like that. And this doesn't have a top or a bottom. It just goes infinitely in both directions. something like that. Well, does this meet the criteria that we've listed up above? So a line, it has to be the collection of all lines where they lie parallel to a given line in space. Right? Well, they're certainly all parallel to a line that's vertical. Right? They also have to pass through a given plane curve. Well, the plane curve that they all kind of pass through is this circle curve. All of the lines end up passing through this line. So if I go from here out to here, I end up passing through this, but I'm still parallel with the vector that's pointed straight up. So yeah, the conventional idea of a cylinder is basically the equivalent of a math cylinder, but there's more. Let's look at another shape that you might consider. So consider an R3, the curve y is equal to x squared. So again, let's kind of draw out our axes, right? And then here we go. So now this time in the xy plane, this looks like a parabola, right? And there's no restriction on z, so it goes infinite in the z direction. And I will try my best here. So we have some kind of parabola in the xy plane, like this. What we'll do is we'll just copy and paste this same shape, but we'll move it up some. Oop, now we're way too far up. Okay, let's move this down. Like that. Now we'll use a straight line. Connect these guys. Ah, it doesn't look so bad. So now we've got this strip here, right? Does this meet the criteria? We have to have that all the lines are parallel to another given line. Well, these are all still vertical, right? They're all still parallel with a vertical line. They also all have to pass through the same plane curve. Well, they all pass through the curve in R2 in the xy plane. Y is equal to x squared, right? So if we look down here, that this is just, if we think about in this plane, y, oh, still a straight line. There we go. Y is equal to x squared in this xy plane here. These all still pass through that line, right? Up here, it was a circle or an ellipse, and this was a cylinder. Here, it passes through y is equal to x squared. This is still a cylinder. The way that we've defined a cylinder here, this curve, this surface is still a cylinder. It still abides by these two rules. It has all the collections of the lines, they're all parallel with the given line in space, and they also pass through a plane curve. This y is equal to x squared. So, in fact, this has a specific name. This is a parabolic cylinder. So let's actually define this guy as well. If this is a parabolic cylinder, the thing that we kind of think of generically as a cylinder, this is an elliptic cylinder. Okay, let's do another sketch here. Let's make one last cylinder. This time, let's look at y squared minus z squared is equal to 1. And I'll try my best at kind of drawing this. So I think I want the negative y as well here. And that x or y is equal to 1 and y is equal to negative 1, we kind of have, okay, shape maybe like this. And we're kind of looking at it at an angle here. So it kind of comes up maybe like that. This one kind of like that. So this is not the best drawing, but imagine that we have this like hyperbolic shape, right? Kind of defined by the first lines that I drew here. And we're looking at an angle, so we kind of have all these lines that are parallel that go along this surface here. Oh, that one's not too parallel. It doesn't matter. Right? And then we have some moving over this way. But all of these lines, this collection of lines, they're all parallel to some vector that's pointed in this direction. In fact, they're all parallel with the x-axis. And the planar curves that they follow is defined by this hyperbolic-like shape here, right? This y squared minus z squared in the yz plane. This here is a hyperbolic cylinder. And of course, you can have any kind of planar curve that kind of defines these cylinders, but here's just 3 that have specific names. We have the elliptic, we have the parabolic, and here's the hyperbolic cylinder. So an equation in any 2 of the 3 Cartesian coordinates defines a cylinder parallel to the axis of the 3rd coordinate. So this one here This is a cylinder because it only used y and z, just 2 out of the 3. And because we were missing x, this is all parallel with the x-axis. Now up here, we have y is equal to x squared. So we're missing our z. So this is a cylinder that is parallel to the z-axis. Okay. So those were cylinders. It is 1:25 right now. So why don't we take our 5-minute break, and then we can come back and talk about quadric surfaces. So go ahead, get yourself some water, go use the restroom if you need to, and we'll be right back. Oh, sorry. I keep doing that. Keep muting myself. Yep. I got about 5 comments just now. Sorry about that. There was a comment earlier about if there was a plus or a minus here. The book defines D to be the negative version of the one that we've described here. So we're just flipping the sign on this right here. Your book has a positive because their D is negative. Okay, so now we were talking about, oh, let's just do a new page. We're talking about quadratic surfaces. Get situated here. Okay. So give myself some room here. The general form of a quadric surface is, all right, we got to leave ourselves a good amount of room here. We have a x squared plus b y squared plus c squared plus d xy plus e yz plus f xz plus g times x plus h times y plus j times z plus k is equal to 0. So that's all combinations up to power 2 here, right? So we have x, y, and z all squared. We also have powers of 2 in the polynomial terms x, y, y, z, x, z. And then we have our linear terms, x, y, and z, and then our constant term here. Okay, so any surface that takes something of this form, some of these might be 0, but as long as we have, these are the only terms that are included in our expression, this describes a quadric surface. So a lot of different surfaces kind of fit this definition, and they all behave very differently. and we'll kind of look at a few that we should be able to name going forward, right? So notice that if I let all of the power 2 terms go away, if I all A, B, C, D, E, F, all be 0, right? And then maybe I've got some in here that I cut out one of these. I'm left with the equation of a plane, right? So a plane is a quadric surface. You can also put some cylinders into this category as well, right? We said that x is equal to y squared was a cylinder. That fits in here, right? But that doesn't mean that all cylinders are quadric surfaces, and this doesn't mean that all quadric surfaces are cylinders. Right? They just have some overlap. So to define more curves, we will also use cross sections. Or another word for that is traces. So we're going to go through a few examples, and we're going to swap back and forth through on Mathematica, so I can show you a plot of what these things look like. We're going to kind of get an idea. So let's start here with the ellipsoid. Okay, so the ellipsoid follows a general pattern where I have an x squared over an a squared, followed by a y squared over a b squared, then a z squared over a c squared is equal to 1. Okay, so you might be thinking to yourself, if I cut out this z term and I just had x and y, so think back to just to R2 for a second, that's the equation of an ellipse in R2. And we tack on this z term here, and we've created ourselves an ellipsoid. So this is kind of the generalization of an ellipse from R2 to an ellipsoid of R3. Another way to kind of figure out what these things might look like is take these slices or traces. So think what happens if I let z be 0, right? Basically eliminating z from the equation. Well, the resulting thing in the xy plane is an ellipse, right? And if you cut any one of these variables out, let's say you let x be 0 or y be 0, you also get an ellipse in the corresponding plane. So if you let y be 0, you get an ellipse in the xz plane. And if you let x be 0, you get an ellipse in the y. If you let x be 0, there's an ellipse in the yz plane, right? So all of the traces are ellipses. So we're going to look at an example here. An example where we have x squared plus y squared over 4 plus z squared is equal to 1. Okay, so let's try this out for the first time. Let's do a new share, and we're going to pull up a Mathematica. Now, do you guys see Mathematica here? I just want to confirm if you're in chat. Yes, okay, perfect. Okay, so the first thing up here, and if you guys know Mathematica, or maybe you don't use Mathematica, Mathematica is pretty powerful, especially in this class. It It's usually linked with this class when we do labs, but we kind of cut those out last semester, and we're continuing that idea this semester. But yeah, Mathematica is really powerful. It helps you kind of visualize things pretty easily. And it helps you do a lot of symbolic solving. So here I'm doing a contour plot in 3D, and see here I have my x squared plus y squared over 4 plus z squared is equal to 1. And let's go ahead and plot that guy. So here is my ellipsoid. Looks like a football, right? So I kind of just spin it around a little bit. And you can imagine that the stretching in that one dimension there is due to the fact that I put y squared over 4. So if I eliminate that guy, and then it's just x squared plus y squared plus z squared is equal to 1, ta-da, you can imagine that I get just the sphere of radius 1. That's the equation of the sphere. But as soon as I put in a kind of elongation here, right, and I now kind of elongated in the y direction, and maybe I do it on another term. So now it kind of looks like I stepped on the football, right? I squished it out. Okay, so this is an ellipsoid. So now let's go back, new share. Let's go back to our display here. And now let's look at an elliptic paraboloid. So the general form of an elliptic paraboloid is I have an x squared over an a squared plus a y squared over a b squared, and this is equal to z over c. So notice here that my z term is not squared, so I just have x squared, and I have a y squared term, but I also just have this linear term on this right-hand side. Okay, so let's kind of think about what happens if we look at these traces by setting some of these to 0. If you set z equal to 0, you're kind of thinking about what happens if you kind of took a horizontal knife and you just kind of sliced this object, right? So we can kind of think of horizontal traces. So the horizontal traces are ellipses, right? Because I just kind of cut this z term out, or maybe even just make it some constant that's non-zero. It's still an ellipse. So what happens if I think about these vertical traces, right? If I let x or y be 0, I'm kind of cutting it in either the x direction or the y direction, but I'm kind of seeing what this looks like along the x-axis or along the y-axis, right? So if I cut one of those out, I've just got this. Let's say we cut y out here. We set y equal to 0. We get x squared over a squared is equal to z over c. Well, in the xz plane, that should look like a parabola, right? I've got z equal to some x squared with some constants, right? So the vertical traces are parabolas. Hence the name. Elliptic, we got ellipses in this one direction, and then paraboloid because of the parabolas in the other direction. So another little tidbit to kind of help us draw this is the first power, meaning the linear term, defines the axis of the paraboloid. So what do I mean by that? See, up here I have the z is the linear term, right? But that doesn't always need to be the case. Maybe I had that the z term was squared, but I had that the y term was linear, right? So that will kind of morph the paraboloid in that corresponding direction. So let's kind of look at an example here. We're going to look at x squared plus y squared is equal to z. So pretty simple. So let's do a new share. We're going to go back to our Mathematica. So here I have my x squared plus y squared is equal to z here. And this is what it looks like. So imagine that we let z equal 0 or some constant, so we're slicing it horizontally. We can kind of look at the traces from up above, right? You get this circle because we have this x squared plus y squared is equal to some constant, right? When z is some constant value. Okay. So if I put maybe this over 4, and I didn't make my range a little bit too small, but you can imagine that this is just kind of like a parabola in this one direction, and it keeps going. And here's another parabola in this other direction. But if we look from above, we get ellipses. And let's kind of change this up a bit to see what happens at the other term. So we get z, let's make it a circle again, and we'll put a y over here. Ooh, and let's change our domain just a little bit. There we go. So again, we have circles now in the xz plane, but where this like cone or this bowl kind of shape is opening up in the y direction, right? And that's what I meant by that linear term, kind of morphing it into a different direction. So let's go back to our page here. So now we're going to talk about hyperbolic paraboloid. You can imagine what kind of traces we might expect just based off of the name. So let's look at the form here. We'll have an x squared over an a squared minus a y squared over a b squared is equal to z over c. Okay, so a little bit different. I still have my x squareds, my y squareds, and some linear term that we can obviously switch out. This is just one form of it. But now I've got this minus sign out in front of one of the second power terms. So let's kind of think about these traces. If I let z be 0, we're looking at the horizontal trace of this object, right? Or in fact, if we let z be some constant, we get hyperbolas. So we have a horizontal trace and now if we say we cut out one of these x's or y's, so if I let x be 0 or I let y be 0, we get parabolas again. So we have that the vertical traces are parabolas. And you can imagine we can actually just copy and paste this whole phrase right here. This is the same little tidbit that we can place in for this guy here. The linear term here defines the axis of the parabolic trace. Just move to B. Okay, so let's look at an example of this guy. So our example here will be x squared minus y squared is equal to z. So now let's go up and pull up Mathematica once again. And now we're looking at x squared minus y squared is equal to z. And this is what we have. Oh, this is way different if I had that plus sign. Right, it kind of looks like this saddle. Right, so what happens if we kind of think about if we cut this across here, right? So basically maybe if we like look at it, well, if we kind of cut through it, you can kind of see these lines, right? This would be the left side. And then over here, if we cut through it, you'll have these other horizontal lines. So we'll get this hyperbola-like shape, right? And if we cut it vertically, you can kind of see these lines here. This is why we kind of use contour plot in Mathematica. You can kind of see that this line right here, this is a parabola. So if I cut it down vertically here, I get this parabola. And likewise, if I cut it maybe across this way, you can kind of see that these are also parabolas. Right, so I have parabolas, and then I also have hyperbolas, so I get this saddle-like surface. Pretty cool, right? All we had to do was just switch this positive to a negative, and we've gone from this really nice looking cone out to this saddle looking object, right? So just changing a few different things dramatically changes these surfaces. Okay, so let's go back to our whiteboard. We have a few more. So this time, let's talk about the elliptic cone. So the elliptic cone will have an x squared over a squared plus a y squared over b squared is equal to a z squared over c squared. So kind of almost the forms that we were talking about before, but now we don't have a linear term anymore. We just have this z squared here. So this kind of differs from our ellipsoid here because we don't have a constant term. And in fact, we've got a negative out in front of that z squared. So we just moved it over to the other side. So what's happening here? Well, if I let z be 0, it looks like my left-hand side kind of indicates that I should be looking at ellipses in the xy plane. So the horizontal traces are ellipses. And if I let either x or y be 0, so we're looking at these vertical traces, well, now I've got like an x squared is equal to the z squared. This is an indication that I have some more hyperbolas. So I have that vertical traces hyperbolas, except, we should kind of mention this, except when x or y is equal to 0. And we'll kind of see why that kind of happens here. We can't have, I guess we can't set either of these to 0, but we can set them to a constant in order to get that trace. And we'll look at what our example looks like to get a good feel of why we can't have x or y be 0 here. Okay, and what's our example? Our example is our x squared plus y squared is equal to z squared. So here we have our elliptic cone. Pretty cool, right? If we look from the traces horizontally, these are definitely circles. And if we look at these traces that don't pass through the origin that are cut vertically, you can kind of see these lines here. These are hyperbolas. But we can't have a trace that goes kind of past through the origin here, because then we'll just be left with a point, right? And in fact, if we do the vertical traces, not just the horizontal trace that gives us the point, but if we do the vertical traces along there, we end up with these straight lines that kind of define the outside of these cones. Right? And that makes sense. If we completely eliminate x or y, we just get this x squared and z squared, right? We can take a square root of both sides and make sure we get the plus or minus of that, but it will end up just being the equation of these lines. Okay, so let's go back to our whiteboard. We're almost done kind of defining these shapes. Got two more. This is the hyperboloid of one sheet. So this guy takes the form of x squared over a squared plus y squared over b squared minus z squared over c squared is equal to 1. So very similar to our elliptic cone here, except now I just have a constant term that's introduced. I just added this 1. Okay. So if I eliminate this z, or I let it to some constant value, right? The thing that I'm looking at are ellipses, right? So I have a horizontal, traces are ellipses. But once again, if I let either of these x or y's be a constant value, I end up with more hyperbolas. So I get the vertical traces hyperbolas. There we go. And there's one more thing to note on this one, is that the negative coefficient indicates the axis of symmetry. So what do I mean by the negative coefficient out in front? It's just the way that I've written it here is in front of the z term, but we could have had it perhaps in front of the y term or the x term. And we'll kind of see why this is the axis of symmetry when we do a plot of our example, which is our x squared plus y squared minus c squared is equal to 1. It's like a funnel, except it's got a big hole. Not a very useful funnel. Just opens back up on the other side. So our horizontal traces, if we just kind of slice through this, you can see our circles. If I slice through vertically, you can kind of see that these lines indicate that we have hyperbolas. And this is one continuous object here, right? So this is why it's called of one sheet, right? And we'll kind of define the two sheet version here. So let's go back to our whiteboard. A hyperboloid of two sheets. So this time our form will have a negative x squared over a squared, a negative y squared over b squared, and a negative c squared. Oh, sorry, it should be probably, I think this is positive, over c squared is equal to 1. So now this time we have two negatives rather than the one negative. So the same traces as the hyperboloid of one sheet are true. So we can even go ahead and copy and paste this whole thing. In fact, or well, let's get rid of the axis of symmetry here. Oh, and I didn't get all of it. The vertical traces. Right, because if I eliminate z, we can move these negatives over, and then we get these ellipses, and our vertical traces are hyperbolas. So now let's look at an example. Where we have negative x squared minus y squared plus a z squared is equal to 1. And this is why it's called of two sheets, because nothing exists in between these two, unlike the one sheet where it's a continuous surface. This has a discontinuity where it kind of just jumps across. Right, and you can still see we have these ellipses. In fact, in this case, we've got circles here. And if we do some vertical slicing, we're going to get some more hyperbolas. Okay, so that's it for those 6 entities. So let's do an example where we would have to classify one. Let's go back to our whiteboard here. We're going to classify the surface that's detailed by x squared plus 2 z squared minus 6x minus y plus 10 is equal to 0. So this is definitely a quadric surface. It fits the description. We have polynomials only up to order 2 here. And we're going to try to kind of massage this into looking like one of the things that we've kind of defined above and classify it. So in order to do so, let's do some completing the square. So the first thing I'm going to do is group all of my x, y, and z terms separately. So I have x squared minus 6x. I also have 2z squared. I also have this negative y. And then I'm going to group my constant term by itself as well. So I have 10 is equal to 0. Okay, so for these x squared terms, or sorry, just these x terms in general, I want an x squared minus 6x. And to complete the square, I need a 9 here. So let's keep that 9 in mind for later. And then for my z terms, well, I actually don't even need to do the complete the square. I just have a z squared here. So we have 2z squared. I don't need to touch the y at all. So here, my constant term, I had 10, but I added 9. So I need to subtract 9 here. And this is still equal to 0. So now here I've got x minus 3 squared plus 2, and I'm kind of write it like this, z squared, plus I still have this negative y, and now I also have this 1 here. Okay. So we take a look at this. Does this kind of match any of the things that we've had above? Well, the one that it's closest to, since we have this quantity that's squared here for x, we have this quantity here for z that's squared. We have a linear term only in y, but then we have this constant term, right? In fact, none of the ones that we classified look exactly like that. But what we have to recognize is that what we could do is write it in this way, where we have x minus 3 squared plus 2 times z squared equals, I'm going to move this y and this 1 over, and I'm going to write it in parentheses to kind of keep us thinking about them grouped. This is y minus 1. So there is a category that fits having two things squared. We have this x quantity squared and the z quantity squared, and then we had a linear term. That was an elliptic paraboloid, right? So what we can do is think of this minus 3 and this minus 1 here as a shift. We're taking our elliptic paraboloid that is, air quotes, centered at the origin, and we're transitioning it over by this shift here. So we're shifting so this means that it's shifted in x. This means that it's shifted in y. And this is the form of an x squared over an a squared plus a z squared over a c squared is equal to y over b. So this is an elliptic paraboloid on the y-axis, because the linear term was the y1 here. Okay, so that wraps up section 10.6. So we're actually a little bit ahead. We're probably half a section ahead right now. Good, because that will give us a little bit of time for some of the tougher stuff later on in the course. If you don't have any other questions, then I say let's head towards the weekend, and then we can reconvene on Monday.